Hello and welcome everyone to this session of the series where we are trying to learn about agentic workflows using LangGraph. In the last session, we built from the bottom to the top and we reached the point where we learned about React Agent, how to build the React Agent in LangGraph. And in this session, today we are going to learn how to enable our React Agent with memory. Now, what is memory? Why do we need memory? So I'll take you to the code section immediately. We're going to start with it. Now I have pre-written these codes for you. I'm not going to write them today, because I'm trying to save time and it'll be benefit for you as well. Okay. So we are going to try to enable our React agent with some memory. Let's see what I mean by it and how do we do it. Let's start with creating the React agent again. So we did this in the last session, but I'm repeating it just to avoid any confusion. So we start with defining the tools, the multiply tool, the add tool, and the divide tool. We assign them as tools using the structured tool class. Then we create the tools list and we bind these tools to the LLM. After that, we create the state, we define the state class, and we define a system message. You're a helpful assistant tasked with performing arithmetic on a set of inputs. And then we define the assistant node function, that is the LLM node. It's basically taking in the state and providing the response from the LLM. The response can be a tool call, it can be a generic LLM response as well. We saw that. And after that, we just create the builder object and we add nodes and edges to it. All of these we covered in the last session. And then we created the React graph. This is how it looked like. Now if you try to execute it with something like multiply 3 and 6, it generates a tool call. It calls the multiply tool and we get the response 18 from the tool, and that particular response is again transferred back to the LLM to get this response. The result of multiplying 3 and 6 is 18. This is the final response that we got from this. Now what is the need of adding memory to this? Now say that whenever we use a ChatGPT or any other LLM, we always try to hold conversations with it, right? So say that if I go to ChatGPT and I type I want to learn about Python, and it gave me some information about Python. Then what I can do is I can ask follow-up questions based on my conversation, and it already knows what I'm talking about, right? It's because it is storing our conversation in its memory, so that it gets the context whenever I'm talking to it. Let's see what it means over here. Now that we have executed our React graph once with this particular query multiply 3 and 6, I'm trying to execute it again with this particular query. Now add 2 to it. What I mean by this is I got the answer as 18. Now I want it to add 2 to this number, and the answer expected is 20, right? You know that ChatGPT should be able to do this, right, easily, because it has memory feature in it in the backend. But let's see what happens here. Let's run this. The human message is add 2 to it. AI message is it is calling upon the add tool, which is good. But look at the arguments, guys. It knows that one of the arguments is 2, but it is taking the second argument as something as 5, right? Which is not correct. Why? Because it does not understand when we write add 2 to it. It does not understand what is this it part. We know that the it is 18, right? We are basically asking it to add 2 to 18, but it does not comprehend that because it is unaware of the previous execution. So we can say that every single execution of the graph is in a transient state, which means that every single execution has its state, but that state gets lost once we shift to another execution. So the state of this particular execution is basically lost as soon as we execute the graph again. So to add memory to it would mean that the state does not get lost and it gets carried forward in the subsequent executions of the graph, so that the context is maintained and we can hold conversations in our graph. So it added 5 and 2 to get the answer as 7, which is completely wrong. Now we go towards adding memory to our graph. So how does it happen? LangGraph uses a checkpointer to save the state after each node or step. We're going to use the memory saver checkpointer, which is an in-memory key value store for storing graph states. Now in LangGraph, we have multiple ways of storing the states or enabling the memory feature. One of those is the memory saver. We're going to see how the memory saver works today, and the memory saver is basically a key value store, and it is an in-memory key value store that helps us store the different graph states. Let us see how it works. So I'll try to explain to you how does memory works in LangGraph. Look at this particular graph. A very simple graph starts at this point with a state, goes to node 1, which updates its state, and then it goes to node 2, which again updates its state, and then it goes to end. Now every single state is stored in something called as checkpoints. So you can understand that memory in LangGraph is stored in the form of checkpoints. So every single checkpoint is basically the state at each step of the graph alongside some metadata. I'll try to zoom in here. You can see when the graph executed node 1, it got an updated state and it stored it in a checkpoint, and the checkpoint looks like this. So the state is the dictionary, and say we have just added some arbitrary states over here. State is IAM, and it also has some metadata associated with that state. It can be what is the next node, what is the ID of this checkpoint, stuff like that. And then again the graph goes to node 2, executes it, and then again the updated state is stored in another checkpoint, which is I am happy over here. And then again it also stores some metadata related to that particular state. Cool. Now all these checkpoints are basically stored in the form of a thread. You can understand that thread is basically a collection of checkpoints. So whenever we run a graph, say that it has multiple nodes, around 4 to 5 nodes, or if we go here in this React agent, we have this node, we have this node. What happens is that every single node's output, or whenever the state gets updated, it is stored in the form of a checkpoint and then in the form of a thread, which is a collection of checkpoints. Therefore, there are two things that we need to take care of whenever we are enabling the memory feature in our graph. First is the checkpoint feature. Second is the thread. So we need to ensure that each state is being stored in a checkpoint, and we need to ensure that all those checkpoints are being collected in a particular thread through which we can access all those checkpoints. Therefore, we need to configure a thread in order to use the checkpointer feature in our graph. All the checkpoints for that graph is stored under that thread ID. All right, now let's configure it. So We import the memory saver module from LangGraph.checkpoint.memory, and we initiate the memory saver object. After that, we assign the checkpointer feature to our graph while compiling the builder object. I'm naming my particular graph as React Graph Memory, and while compiling it, I'm adding this input parameter now, which is checkpointer, and I'm assigning it as the memory store which I'm going to use. So I've configured the checkpointer feature right now. Now we need to configure the thread feature that will hold all our checkpoints together in a collection form. So while configuring a thread, we need to assign a thread ID, which is the bare minimum that we need to assign. You can assign it as 1, 2, 3, whatever you like. Thread ID is basically required so that we can access that particular thread and all the checkpoints stored in that thread using this thread ID. Now I'm again trying to execute our React graph. So the message is going to be the same. The input message is going to be multiply 3 and 6, and I invoke it with this particular input. But while invoking it, I add this extra parameter here, which is the thread configuration. So we configure the thread over here, we configure the checkpointer over here, and while invoking, we are adding this particular thread configuration as an input parameter. Then we execute it again. You see, it's the same as before. Multiply 3 and 6. It called the tool multiply, got the answer as 18, and this is the final response, result of multiplying 3 and 6 is 18. But here is where the story unfolds. Now we are again executing the same graph, React Graph Memory, with this particular message. Now add 2 to it. Let's see how this one performs now. So you see, it starts off with the same human message that we provided earlier. It means that it remembers the conversation that happened between us and the graph earlier, because that conversation has been stored in the form of checkpoints in our particular thread. So starts off with human message, multiply 3 and 6, multiply tool called, we got the answer as 18. Then I added another human message, add 2 to it, and it decided to call the add tool, and now it exactly knows what it means because it is aware of the previous conversations that we had with this graph. This is the power of memory in graphs. And now it has called the right tool with the right arguments, and it got the answer as 20. And again, because it's a React agent, it again sent this particular value to the LLM node, and we got this response, adding 2 to the result of multiply 3. Now that we know that it works, we can try with other inputs as well on top of this query. Let's try with something like this. Now multiply that by 0, and so the answer that we should get is 0, right? Because 20 multiplied by 0 is 0. Let's see what happens. Starting from the top, the first human message is multiply 3 and 6. We got the answer as 18. And the second human message is now add 2 to it, and we got 20 as the answer. Now the third human message that we provided again is multiply that by 0, calling the multiply tool, multiplying these two, and we are getting the answer as 0. So cool. Now we understand that how memory can be enabled in graphs. We will learn about more techniques about how to enhance our graphs using different techniques like human in the loop, and how to play around with some complicated graphs and create some real, creative graphs. So stay connected in this playlist, and more interesting sessions coming up for you. Thanks for watching.